Okay, now we will continue. So here we have um, the rotor. So this is one typical rotor, and this is another one here. So we will align them the same way. So these are two typical rotors. So as you can see, here we have, this is called a slot, and inside this slot we put our coil. So here we have the coil, and to close the slot we have a wooden key. Okay, so this is a key to close the slot. So actually the slot is something like this. So you put the coil inside the slot. So you put the coil inside the slot, and then you close the slot using a wooden key. This is a key, so you can keep the wires in place while the machine is rotating. So these are the coils, and this is the key, and this is the slot, and this is the teeth. Okay, so this top part here is called the teeth. This engraved slot here is the slot, and this brown part here is actually the wooden key that closes the slot, and you can see that the wooden key is larger than the slot. Okay, so you can look here, so you can see here that this is closed by a key, so we can keep the coil in place. So these are the keys. Sorry. So these are the keys. Okay, and this is the coil, and you can see that this the rotor here is laminated. Okay, and this is very important note, that the rotor body is laminated. Okay, and here we have a question here, why the rotor body is laminated. Okay, and this part here is the commutator. And last lecture we explained what is the importance of the commutator, and this part here also is the commutator. And here we have the bearing. Okay, so you can keep the shaft in place. Okay, this is the shaft where you will couple your mechanical load, and you can see that the coils are attached to the slots, and here between these segments there is insulation. Okay, so this is insulation. You can see here the tin used to solder the coil into the segment, and you can tell if you compare these two machines that this machine is more efficient because the segment size here is smaller, so we are expecting lower ripples if we have DC supply, or less vibration if we have torque, if it is a motor. Okay, so this machine has a smoother torque or voltage if it is generator, and torque if it is a motor. Because of the segments are smaller, so the ripples, as we explained last time, will be less. And this part is the brush system. So this part is called the brush system. So here we have, these are the brushes. Here we should have, this is a spring, and this spring is pressing the brush, so the brush will have a good contact with the coil or with the commutator. So this is one brush 1, this is brush 2, and you have here 2 wires, one wire and the other wire here. And this brush system will be attached to the rotor. So let's see here how the brush system is attached to the rotor. Okay, so just we took this part here and we attached it to this part here. So this is the brushes for this rotor. Okay, so you can see that this is the rotor here, this is the armature. Okay, and here we have the commutator, and here this is the brush, and the spring here is pressing the brush, so you have a good contact here. This is good contact. While this machine is running, between the brush and between the commutator at this location here, there will be for sure friction, and there will be heat generated. There will be friction, heat generated at this part, and there will be some arc. That's why DC machine with brushes cannot be used in oil and gas fields, because there is a fire hazard. Okay, so this is the rotor part, or this is the main part of the rotor. The second part, so these are the armature or the rotor and the brush commutator system. Now the second element we need, so we covered the wires, the second element we need is flux. So how we can produce flux? So we have two options. One option is to produce flux using permanent magnet, and the second option is using an electric magnet. So we can produce the flux using a permanent magnet or using an electric magnet, and these are the two rotors we have here. Okay, so this part here, so this is the stator part, and inside here you will put, inside this you will put your rotor, or inside here you will put your rotor. So as you can see here, we have magnets. Okay, so this is permanent magnet. One of these will be north and the other one will be south, and you are producing the flux here. This one here is an electric magnet. So you can see here there is a coil. Here the coil is removed. Coil is removed from here. So you can see the pole structure. So this is the pole, and around this pole you will put your coil. Okay, so which is this one here. So the pole structure, so this is the pole. So we have, this is the pole, and this part is called the pole shoe, and we shape the pole shoe with this shape, and we will see why we shape the pole shoe in this arc shape. And around this pole shoe, or around this pole, you will put your coil. If you supply your coil here from electric current I, you will produce flux phi. Okay, that's why we call it an electric magnet, because the magnet is created using current. You need to supply it. Here it is active, so no need for external source. So permanent magnet, you don't need an external source, but permanent magnet are not controlled and they are weaker. So you cannot control the flux compared to the electric magnet. The electric magnet, you can control the flux by controlling the current, and even you can make this flux so strong because the flux is Ni divided by the reluctance. So adding more turns or increasing the current will give you a powerful magnet. But the cost for electric magnets are more compared to permanent magnet, as you will have to have a technician to build the magnet, and you need to build the structure following this way. You need a pole and pole shoe, which is more expensive compared to a permanent magnet. So the question is why we shape the poles as an arc. So this pole, or under this pole, you will put your rotor part, and your rotor part is a cylinder. So this is a cylinder, this is the rotor. So if you shape the pole the same shape as the rotor, you are keeping a constant air gap between them. So in this case, the air gap is uniform and the flux is uniformly distributed. That's why we form the pole as an arc. If the pole is flat and you have the rotor as a cylinder, you will have large air gap here and a small air gap here. So most of your flux will get crowded in the center, and you will have less flux at the edges, which will cause saturation at the center of the pole, which is not recommended. That's why we keep the air gap length fixed or uniform or constant by forming the pole as the same shape of the rotor. And this is the basic structure for DC machine. Here there is another hint. You can see that the stator is not laminated. So the stator body is solid and not laminated. And I will leave this question for you. Why the stator body is not laminated while the rotor body is laminated? You can see here the laminations of the rotor body. So why the rotor body is laminated, or the armature is laminated, while the stator is not laminated? So this is the full structure of the machine. So this is a typical commercial DC motor, and these are the parts. So you have your shaft, you have the bearing, you have the end bracket, the frame, you have the stator part, the commutator, the brush system or the brush assembly, and the rotor or the armature. Sometimes we call the stator, we call it field, and we call it field because it is the source of flux. So because the stator is the source of flux, we call it field, and the armature is the rotor, but the typical name we use it usually for the rotor is the armature. So this is the basic construction of DC machine. So far we covered the construction of DC machine and theory of operation. Now let's take the equivalent circuit of the machine. So the machine, if the machine is with electric magnet, so we will assume an electric magnet machine. So in this case, the stator here, so the machine has a stator part and this stator part has two terminals, and you have to supply the stator with a current, and the function of supplying the stator with a current is to produce flux. Doesn't matter if you have a motor or generator, you have to establish this flux for motor or generators. So if we go back, if the machine acts as a motor or generator, you need the flux in both cases. For the armature, if you rotate the armature with a prime mover, you will have a generator. If you inject current into the armature, you will have a motor. So motor or generator, it's actually a mode of operation, not a type of machine. So any electrical machine can act as a motor or generator. That's why the hybrid cars or Tesla cars, the machine during braking, it can be converted to generator because it's the same machine. And this is the difference between machine and motor and generator. So the DC machine is a machine which can act as a motor or it can act as generator. If you inject the current into the rotor, it will act as a motor. If you rotate the rotor, it will act as a generator. So if we consider an electric magnet machine with an electric magnet, so the stator is supplied with a current I to generate the flux. Let's remove this. So the machine is supplied with current I to establish the flux. So this current I, we will call it IF. IF. So IF is called field current, and this is the current to establish the magnetic field. Now, if the machine is a permanent magnet machine, in this case, the stator part will have no terminals. So there is no terminals for the stator part because the permanent magnet or the magnets are creating flux without any source. So if you have a magnet, it is producing the flux without any electrical source. And this is the difference between this one here. So there is no wires going out, and this wire here you have wires coming out from the coil. Okay, so here there is no terminals, and here there are terminals. Now, if we look at the rotor in both cases, so the rotor is the same. If you have an electric magnet or permanent magnet, the rotor is the same. So what we have for the rotor, so here we have our commutator, and here you have your coils or the rotor part. So this is a commutator, and around the commutator you have brushes, and if it is a motor, there is a current IA entering, and if it is a generator, there is current IA leaving. So this is generator and this is motor, and we name it IA because this is the armature. This is the armature current, and armature because this is the current going into the rotor. And because the rotor is moving, it will cut the flux phi, and there is a voltage generated here, and we call this voltage EB or back EMF. Back EMF, which we explained in the motor action, that in the motor action, when you move the coil and the coil will cut the flux, it will generate a voltage, and we name this voltage as E or back EMF. So these are the basic parts of the machine. That's why we will sketch the circuit, the equivalent circuit of DC machine. We sketch it as the following. We sketch a source with the value E back, and here we have the two brushes, and this is the equivalent of, and here is the shaft, and this is the equivalent of the rotor. The current here is I armature. So we name this part as armature circuit. And to be more practical, we should add a resistance here, which is the resistance of the wires used here. So here there is coils, and these coils has resistance. So there is a resistance RA, and this is the armature coils resistance. So this is the resistance of the armature coil. Now, if the machine is permanent magnet, just to sketch a flux here phi. But if the machine is an electric magnet, we should sketch another circuit, and this circuit is only a resistance R field and the current I field, and this is the field circuit, which is the circuit here. So the circuit here is just the stator is just a coil. It's just a coil. So this coil is stationary. So this coil is not cutting the flux to generate E. So it's different from the rotor, because the rotor is rotating. So there is EMF induced in the rotor, but there is no EMF induced in the coil of the stator, because it's the stator, it's stationary, it's not moving. So this coil here is just a coil which has a resistance. That's why the field is sketched with a resistance R field. To represent the functionality of the field, I prefer to sketch a coil. Although in DC a coil should be a short circuit, but this is for you to remind you that the function of this part of the circuit is to produce field. So its main function is to produce flux. That's why in the equivalent circuit I love to add a coil. The angle between the armature or the brushes and the field should be 90 degrees. So to be sketching something really correct from the electrical machine perspective, you should sketch the field making 90 degrees with the armature. Okay, this is something for electrical machine guys. So the angle between the coil here, this is the angle of the coil or the field, and the angle of the brushes should be 90 degrees. And this is the main idea of DC machines, is keeping an angle between the flux and the armature or the brushes with 90 degrees, so you are collecting the maximum voltage or the maximum torque. If you remember that E equal BLV sine theta, and the force is BIL sine theta, so this theta is adjusted 90 degrees by keeping an angle 90 degrees between the brushes and the field. So how we do this? So say that the field is vertical. When we insert this part here inside it, we rotate the assembly of the brushes, so the brushes are horizontal while the field is vertical. And by doing this, we are keeping a 90 degree angle between the field and the brushes. And this is a very important point. Any technician opening a DC machine, so if this is a DC machine and this DC machine is closed, so this is a part which has a screw here, and this is the motor, and you need to open the screw, and this part here is the brush. This is the brush part. So this part is where the brushes are. So this part here has the brushes, which is this part over here. This part here, which is the part that opens. You will see here there is a screws, and this part will close here. Okay, so this part will enter here. So if you are opening a DC machine like this, before opening the machine, you make a mark here and a mark here. So when you open it and you return it again, you align the two marks to make sure that the brushes will go back to its correct location, which is 90 degree. If you didn't do this, the torque of the machine will go down, or even the machine will not run. And this is something that the technicians will do when they are maintaining the DC machine or fixing a DC machine. So before opening the cap, which has the brushes, they make a mark on the brush assembly part, and they make a mark on the body of the motor. So when they are closing it back using the screws, they return it again aligned, so the brushes goes to the correct location that it was designed for. So this is the equivalent circuit of the DC machine.